In this video, we will be discussing an attention mechanism for convolutional neural networks, which is referred to as the squeeze and excitation network, in short for SENet. So SENet is a mechanism for incorporating channel-wise attention into convolutional neural networks. The motivation for incorporating this type of channel-wise attention is that poor weightings of channels make image recognition harder in convolutional neural networks. And in many applications, some channels are inherently more important than others, and in such cases, attention helps. As an example here, I've shown an example of a figure in which I have an X marked in one of the on the figure on the left. And as you can see, by changing the color scheme, that is by changing the weights of the different colors, suddenly the X becomes much clearer. So here, what we are doing is that we are emphasizing some of the colors for better discrimination of the key characteristics by reweighting the channels. Now, this type of approach is actually often applied to the hidden layers. So in the hidden layers, you will often have complex features, such as, for example, features corresponding to facial features, such as the features corresponding to the nose. In such cases, a facial recognition task will benefit from focusing on these types of features. And in fact, this type of approach is more important for the later layers in practice. And in fact, it is often not applied to the input layer. However, in this video, we will often show the examples using the input layer because it's easier to visualize in practice. But it should be kept in mind that this example from the input layer is only notional. So there are two kinds of attention that are commonly used in convolutional neural networks, and in fact, any kind of neural network. One is soft attention, and the other is hard attention. Now, hard attention mechanisms use reinforcement learning to focus on specific parts of the image in a discrete way. Whereas soft attention mechanisms, they often use learned weights to weight different parts of the image. So while hard attention often applies to the spatial character of the image, it's usually used for spatial character of the image. Soft attention can be used both for spatial characteristics as well as the channel-wise characteristics. So one example of an attention mechanism which performs spatial attention is what is called the spatial transformer. This particular approach is discussed in a different video, and what it does is that it remaps or crops pixels. And the principle of the spatial transformer is that it transforms each channel of a spatial pixel in the same way. On the other hand, channel-wise attention, which is the focus of this video, which is essentially SENet, it weights the different channels. So for example, for the input layer, it means the red, green, blue color maps, and it weights each spatial pixel in that particular channel in the same way. And the SENet can be integrated with any architecture. And this was the winning entry of the ImageNet classification contest in 2017. Now, one very desirable characteristic of SENets is that it is a modular way of incorporating attention. What this means is that it's not a neural network in its own right. It's essentially a module that you can incorporate in any existing neural network. And what it does is it produces an output block, which is the same size as that of the input. So you insert this module between any pair of convolutional neural networks, and that's very similar to a spatial transformer, which is also very modular, very similar kind of principle. And there is no change to the existing architecture other than insertion of the SENet module, because it's producing an output block, which is the same size as the input. So all you do is you insert the module and you keep the rest of the architecture as it is. So what this means in practice is that you can use this for any existing convolutional neural network architecture, which is also generally true of the spatial transformer, which is discussed in another video. So let's look a little bit about what the SENet module can do. What it can do is that it can change the weights of the different channels. And by doing so, it pays differential attention to different feature maps. And this approach, in a sense, it's sensitive to the data set, task, or the specific image at hand because it learns from the data. The module has its own parameters which are learned during the training phase in a data-driven manner. And this is, since the module is incorporated in all the layers, typically all the layers of convolutional neural network, other than just after the input layer typically, what it does is that in the earlier layers, the weights for the primitive features, such as, for example, the lines, are very similar across the different classes. So this is because primitive features, they apply more or less indiscriminately to all the different classes. On the other hand, if you look at the later layers where you have more complex features, such as, for example, in a facial recognition application, you may have nose features. The weights for the different features will be quite different. So the weights for the complex features, so if you have a facial recognition application, the nose feature would be different than, say, a window feature. Now, let's talk a little bit about the architecture and the components of the SENet module. So it has three main components. One is the squeeze module, the other is the excitation module, and the third is the reweighting module. So what the squeeze module does is that it averages the pixel values in each of the feature maps. So for example, again, as a notional example, let's say that you did this to the input layer, the RGB color map. So what it would do is that it would calculate the average R intensity, it would calculate the average G intensity, and it would capture the average B intensity, the blue intensity. Of course, you typically do this to hidden layers, but again, it's easier to understand if I use the example of the input layer. Then the next phase is to use the excitation, which is essentially a shallow neural network, which is shaped like an autoencoder. So what it does is that it's a two-layer neural network with a constricted layer in the middle, with a constricted hidden layer. Typically, you are applying it to the input will be a feature map of reasonable dimensionality because you are typically applying it to the hidden layer of a neural network. So let's say the dimension is 256. It will reduce the dimensionality by a factor of 16. So it will reduce the dimensionality to 16, and then will remap it back in the second layer to again a dimension of 256. So you get exactly as many outputs as the number of inputs, and there's a one-to-one correspondence between the inputs and the outputs. And I've shown the functional form of the neural network here. It has a ReLU in the hidden layer and a sigmoid in the outer layer. So because you're using a sigmoid in the output layer, you will get the outputs will all be values between 0 and 1, which are basically your channel weights. And once you get these channel weights, you reweight each pixel in that particular feature map with that channel weight. So here I have shown the reweighting formula H prime IJP will be HIJP multiplied by the weight of that channel. And the weight of the channel was learned by the shallow neural network from the input features. So there are quite a few experiments for this paper that are shown in the CVPR paper. That's the last bullet point I've shown over here. And you can go to this paper to look at the experiments. The key takeaway from the experiment is, first of all, this was a winning classification entry in the ImageNet classification task. And it achieved a top 5 error rate of only 2.25%, which was quite an improvement at the time. And the approach, as I said before, it can be integrated with any architecture. And at that time, since ResNet was a state of the art, they chose to integrate with ResNet, and it provided a significant improvement by applying this model. So in that sense, it has a meta-learner characteristic where you can apply it to any existing neural network, and it improves the accuracy of the approach. Now, in another video, I've talked about the spatial transformer. I just wanted to show their architecture side by side. The principles in the two cases are very similar. They just do different types of transformation of on the images. So a spatial transformation performs spatial transformation. It will rotate the image, translate the image, magnify the image, whereas the SENet works on the channel wise weighting. So they're both similar architecture with modularity. They have a meta-learner type quality in the sense that you can improve any learner by inserting it into the learner. And they are complementary forms of attention, and they can even be used in combination.